All right, so maybe I'll get started with the introduction. So Chelsea is an assistant professor at Stanford University in the computer science department and also in the electrical engineering department. She also spent some time at the Google Deepmind robotics team. So Chelsea's group works on robots and interactive agents with the ability to generalize broadly to new environments and to new tasks. And today she's going to tell us about different ways of achieving auto-distribution generalization in robotics. So Chelsea, thanks so much for taking the time to join us.
Awesome. Thank you for the introduction. So today I'm going to be talking about generalizing auto-distribution. I didn't come up with a very creative title, but I'll primarily be focusing on robot arms and manipulation, and hopefully when Drago speaks, he'll give a perspective from driving as well. So there we go. So what can robots do today? So and not just today, also several years ago. So this first video is showing a robot using a spatula to lift an object. This more recent video, we trained a robot to tear off a piece of tape and put it on a box. We've also, of course, seen really impressive stunts by Boston Dynamics robots as well. So looking at these videos, I think that if you are not an expert in the field, you would probably think that we've made a lot of progress in robotics, and we probably should be able to actually deploy these robots in our everyday lives. But the catch is that these systems are trained and are effective in fairly narrow environments. So the Boston Dynamics scenario is a robot that was manually tuned for a particular environment, and the videos on the left are robots that were trained with less than 1 hour of data. And while efficiency is often viewed as a good thing, in this case, I actually view it as a bad thing because the robot's experience is really only in that one single environment, and it has no idea how to generally lift spatulas, use spatulas to lift objects. It only really knows how to lift that spatula in that environment for that object, and likewise for that tape canister and so forth. So I think right now, today, robots can perform complex maneuvers in narrow and controlled environments. And for a long time, I've been pretty interested in this question of how we might allow robots to generalize to the real world. And as I mentioned, I think the big problem is that we often try to train robots on a pretty narrow distribution, like in our lab environments, and hope that one day they might be able to generalize to the real world with lots of different spatulas, lots of different environments and objects. So I think this brings us to a conundrum because the collecting really broad training distribution is challenging, and also bridging this gap from a narrow training distribution to the real world is also really challenging. So to start to bridge this gap, what I currently think we need to do is, first, I think we need to figure out how to leverage a larger, broader data distribution to push this apart. And I think there's actually a number of ways that we can do that. We don't have to necessarily, for example, collect a lot of online data. We could leverage data that already exists. And arguably, training on a broader data set is one of the recipes that has led to the success of other systems in AI, like language models and image models. And so I think that this will be necessary for actually allowing robots to generalize in the wild, but not really sufficient. And to actually get robots to generalize to the real world, I think that we need to also figure out how to get robots to extrapolate beyond the training distribution. And this, I think, is in some ways, I mean, the first part has some challenges, but this second part, I think, is actually a lot trickier to accomplish because we need to go beyond the typical kind of standard IID train test setting. And I think it's particularly tricky because environments and objects can change in so many different ways. I don't think we can even hope to anticipate the full range of scenarios and the full range of things that the robot might encounter when it's deployed. And so as a result of this, what I'm most optimistic about when it comes to extrapolation is actually trying to see if we can also train at test time too. And if we also do some amount of training at test time, this means that the robot can actually collect data in the test environment and adapt to that test environment as a result. And then we don't have to try to kind of go beyond necessarily the setting where machine learning works, and essentially kind of adapt to the data that we're collecting and to the particular test scenario. So in this talk, I'll talk about basically two approaches that mimic those two threads. The first will be trying to leverage internet data that allows us to broaden the data distribution that robots are trained on. And the second will be by trying to adapt at test time using data collected during deployment. Cool. So let's start by the first bit. So as some background, we're going to be looking at an imitation learning approach based off of the RT1 architecture, which is a robotics transformer. It's an image and language conditioned policy that predicts, given a language instruction and a history of images, what is the end effector action to take. And it was trained on around 130,000 episodes, spanning actually a fairly long period of time. Now, the RT1 architecture at the time was actually fairly competent, but there's a number of tasks that it can't solve. And as an example of a task that it can't solve, is pick up the whisk. Now, on the surface, this task doesn't seem very challenging. It doesn't seem like it should be a challenge task. It's pretty basic. But the reason why this is challenging is that in the robot's training data, it hasn't ever encountered whisks before. And so it doesn't actually even know what a whisk is. And as a result, this language instruction is outside of the distribution that the robot was trained on. And so for handling this novel semantic concepts, I think that leveraging internet data is quite promising, because while our robot data won't necessarily cover all of the semantic concepts that we might care about, and indeed, I personally haven't encountered all of the semantic concepts that I understand, the internet does actually contain a very broad range of semantic concepts. And with this, both humans and robots can learn about things that they haven't experienced firsthand. Cool, and especially in a plethora of static image data, not just in videos, for example. So I think that if we can combine the robot's experience with this broad internet data, we might be able to get this sort of semantic generalization to out of distribution instructions. And this brings us up this question of how we do that. How do we combine the visuomotor experience from the robot's perspective with the semantics that comes from broad internet data? Now, one really old solution for doing this would be to use a pipelined approach, where you first have an object detector that produces some representation of your state. And this could be trained on static data. And then you have a planner or a policy that operates on top of the detected object positions. Now, one of the things that's nice about this sort of solution is that it actually can solve this problem of picking up the whisk. Because the object detector is trained on, can be trained on lots of static data and have lots of different concepts that the robot hasn't experienced firsthand. But the downside is that first, the planner or the policy is going to rely on very precise localization of the object by that first object detector. And it's also going to throw away other information in the image and the sensory observations that might be useful for solving the task. And lastly, traditionally, object detectors only work with a closed set of objects because they're detecting objects from that fixed set. Now, fortunately, modern VLMs already address this last point very readily and can detect objects with open vocabulary descriptions of the objects. And to address these other 2 points, we'd love to retain the benefits of end-to-end learning, which allows us to learn from raw sensor observations and allows us to figure out a good representation of images that's effective for the task. So our goal is to figure out an approach that can solve the task, retain end-to-end learning, and use some of the benefits of modern vision language models. Now, one solution that's not quite as old for solving this task is clipboard. And the clipboard architecture combined the clip model with an architecture that was designed for the problem. And it actually was also able to solve these tasks with an end-to-end solution. And actually some pretty nice, impressive results of picking and placing different objects or sweeping objects into a table, including objects from novel semantic categories. But I guess the downside of the clip solution is that it's really limited to these sorts of tabletop manipulation tasks with a calibrated top-down camera. And ultimately, we'd love to essentially have a solution that solves these tasks, retains end-to-end learning, and also is applicable to a broader range of manipulation tasks and a broader range of motions. And so our first attempt at this was to look like something like this. And what we did is we took the vision language model, an open vocabulary object detector. This is actually a model that's open source called OWL-VIT. There's also newer versions of these kind of detectors like Grounding Dino. And we use this to detect the objects that are referenced in the instruction and essentially provide a mask that, or a feature map that indicates where the object is located in the image. And then we pass in that mask or that feature map alongside the original RGB image into our policy. And so the output of the frozen VLM is passed into a policy with the original images. And then we train a policy end to end on top of the predictions from the VLM and the images. And what's nice about this is we can essentially retain the benefits of end-to-end learning and use all of the information available in the image, while also benefiting from the semantic knowledge that's contained, semantic knowledge that the VLM possesses. And really the key design choice here is that the VLM is only used to provide the semantic information of kind of connecting the object description to its location in the image, and not actually providing a detailed state representation. Cool. So we refer to this approach as manipulation of open world objects because it allows us to use open vocabulary object detectors to manipulate objects that the robot wasn't trained on or move. And in our experiments, we wanted to train this on data that has physical diversity such that the robot can generalize both physically as well as semantically. So we took the data from the original RT1 training data set, which actually only had around like 17 objects or something like that. So actually pretty narrow in terms of object experience. And then we expanded it to have a much larger number of objects. So adding to around a total of around 100 objects. But for the newly collected data, we didn't want to spend a lot of time collecting data. So we only collected grasping data for those new objects, which is much faster to collect. And so 17 objects have data of all of the skills, and the remaining 83 objects only have grasping data. And this is the demonstration data that we're going to be training the policy on. Cool. So here's a visualization of the objects that were used for training and the fully unseen objects that are going to be used for evaluation, including objects from novel object categories. Now, in terms of the experimental results, we wanted to understand whether or not we can leverage the semantic knowledge from the VLM in enabling the robot to generalize to out-of-distribution objects. And this is the robot setup. We have a 7-degree freedom arm, 2-finger gripper, and importantly, there's distractor objects in the scene. And this really tests the robot's ability to figure out which object it should be interacting with. Without distractor objects, if there's just a single object, then the robot can trivially pick up or manipulate the objects that are in the scene. Cool. And so if we are the main comparison to actually understand the answer to this question is whether or not Mu versus RT1 trained on the same exact data set, what that kind of comparison looks like. And it's also worth noting that RT1 actually uses an ImageNet pre-trained encoder, so it actually does have a lot of kind of knowledge from static image data sets, but that doesn't necessarily mean it will actually be able to leverage that semantic information to solve new tasks. Cool. So here's what the results look like. First, we can look at the grasping results, and we see that for seen objects, both Mu and RT1 are doing quite well for grasping, but for unseen objects on the right, Mu actually enables the robot to grasp unseen object categories with a more than kind of 25 to 30% boost in success rate in comparison to using RT1. When we look at non-pick skills, we see that we get fairly good performance with unseen object skill combinations. And we also see that it's able to perform non-pick skills with completely unseen objects, more than around kind of 10% better than the original RT1 architecture. Now, what about mobile manipulation? So all the results so far were with static manipulation tasks. It turns out there's a prior work called clip-on wheels that can perform open vocabulary object navigation. And so you can combine navigation with manipulation by first doing the navigation and then doing the manipulation to combine naturally cow with moo and get a robot that can both navigate to the to an octopus toy, which is a category that it had never seen in its training data, and pick it up. Cool. The other thing that I'll mention, I didn't have time to incorporate into the slides, but the moo is kind of presenting one way of incorporating the semantic information into these policies. Slightly more recently, the RT2 architecture that we developed also presents a way to incorporate the semantic knowledge in a much more implicit way. And we see the same kind of generalization in the RT2 architecture as well, that's transferring semantics from vision language models, although in that case, closed source vision language models to the real world. One of the nice things about moo is that it's actually using open source VLMs, and so you can actually basically reproduce the results yourself. Awesome. So the takeaways here is that first, end-to-end methods are going to struggle with semantic generalization to beyond the robot data set, and by merging semantic knowledge from VLMs into the robot's policy, we can actually allow robots to generalize out of distribution to new semantic concepts. Now, this is kind of the first approach of leveraging and essentially broadening the data distribution. I think that this will be important, but also, even then, robots might encounter situations that are still out of distribution that you don't anticipate. And so what I'd like to talk about in the second half of the talk is whether the robots can actually adapt at test time from data that they've collected in real time. And the idea is that if we can't anticipate every possible scenario, maybe we can adapt during deployment. And in fact, I think that there's some evidence that humans do something like this as well. So in this video, it's somewhat subtle, but if you watch carefully, when the person is trying to open the door, they actually first put the key in the wrong spot, and then they have to adjust and adapt how their strategy to inserting the key before opening the door successfully. And so in terms of getting this kind of autonomous adaptation, reinforcement learning provides a framework for adapting autonomously in the real world. And so we're going to try to see if we can apply ideas from reinforcement learning to allow robots to adapt during deployment as well. Now, if you look at where we're at with reinforcement learning, when I started working on robot reinforcement learning in 2015, we allowed robots to learn and improve through trial and error like this, where at the very beginning of training, it doesn't know how to solve the task, and it can actually improve from its own experience in the real world. And so this is pretty nice, and it works on real robots, but it's pretty challenging to apply these kinds of reinforcement learning frameworks to deployment time adaptation. And the reason for this is that first, these algorithms need feedback from a reward function, which we don't have access to during deployment. Second, the robot will need to actually have some sort of autonomy in this adaptation process. And oftentimes reinforcement learning in practice isn't actually autonomous. So here's an example of a robot trying to learn how to shoot a hockey puck, and a human is actually resetting and arguably doing more work than the robot. And lastly, we'd like the robot to use prior experience in a way that makes this adaptation really fast during deployment. So one thing you might wonder is, like, in terms of this sort of this autonomy aspect, we just run reinforcement learning algorithms without resets. And even if you take a really simple simulation environment, if you give it resets every 1,000 time steps, it learns well. But as you decrease the frequency of resets, it actually really struggles to learn the task. And this means that existing RL algorithms aren't really well suited for actually autonomous improvement, including during deployment. So this motivates essentially a new problem setting for trying to allow robots to adapt during deployment from their experience. One kind of initial step towards this is called reset-free reinforcement learning, and it allows robots to kind of learn how to do the task and undo the task. But specifically, the kind of reinforcement learning that we'll be looking at is what we call single life reinforcement learning, where you have some prior training data and you want to leverage your prior experience at the task to be able to actually adapt in real time within a single episode to solve the task. And so, so you have your prior training data, and then you encounter a new out of distribution scenario at test time. Your goal is to eventually adapt to that scenario at test time with the experience that you're collecting in that single lifetime to ultimately accomplish the task. Cool. So specifically the problem setting is we're given prior data in a training environment, and then the agent has one life or one episode to autonomously complete the task in a new scenario. As a somewhat simple example of this, we'll start with a simple example in simulation before looking at real world examples. Consider that a robot in simulation that just wants to run forward on flat ground in a training environment. And then at test time, it encounters an obstacle. And we'd like for it to essentially figure out how to handle this obstacle in real time at test time, even though it actually hasn't learned how to handle obstacles during training. Now, one approach you could do is apply RL in a vanilla fashion to this sort of setting and actually try to use RL updates to have it figure this out at test time. And similar to the reset free results that we saw before, you can actually run this, and this is what it looks like. The robot will actually successfully get over the first hurdle, but eventually it kind of gets stuck with the second hurdle and eventually falls on its back. Ideally, the robot would be able to kind of figure out how to get up from here and ultimately get towards the goal. But with reinforcement learning updates in parameter space, the robot isn't able to actually update its behavior enough to allow it to eventually reach the goal. So in order to actually handle this scenario and allow robots to adapt to these kinds of changes, including pretty large changes, we're going to try to essentially not just have the robot adapt at a very low level in the space of parameters or in the space of actions, but also adapt at a much higher level in the space of higher level behavior. And we think that if we allow the robot to adapt both at high levels and at low levels, this might allow the robot to handle big shifts in the environment by more drastically changing its behavior, and also be able to kind of fine tune, make small changes to its behavior that are needed to handle small changes in the environment. Cool. So in terms of how to do this, the problem setting we're going to be considering is we have a bank of pre-trained behaviors, and our goal is to draw upon these pre-trained behaviors within a single episode at test time to handle both typical conditions as well as novel conditions that are out of distribution, like facing ice, like a damaged leg, and like a damaged leg and pulling a box. And ideally, these kind of pre-trained behaviors would form a basis over the kinds of behaviors we might want to combine at test time in order to handle these novel behaviors. Cool. So once we have the pre-trained behaviors, one of our key ideas is to try to leverage the value function of the behavior to figure out which behavior might be relevant at any given point in time. And the intuition here is that if we have a value for, say, the walking behavior, the value should be high if that behavior is going to succeed, and it should be lower if that behavior is less likely to succeed. So this is going to be our starting point. Now, even with these value functions, they may not be very good at, well, first, they may not be well calibrated with one another because they're trained independently for these different tasks. And the second is that even if they are somewhat well calibrated, the states for other skills are going to be somewhat different and kind of out of distribution compared to the states that were used to train that value function. And so one really simple thing that we can do to try to calibrate these value functions across against each other is essentially to kind of further train the value functions to be able to encourage identifiability of states that are familiar. And specifically, the way that we can implement this is we can put essentially a softmax on top of these predicted value estimates to encourage it to be able to predict, to kind of align the distribution of the predicted behaviors with these value functions with the actual behaviors that are recognized. So for example, if you draw a state from the replay buffer of limping, then the value function for that state for limping should be higher on that state than the value function for walking. And so you can essentially add a cross entropy loss to encourage the softmax distribution over values to match whether or not the state came from the corresponding behavior replay buffer. And so it ends up just with a pretty simple objective. You keep on fine-tuning on your offline skill data with Bellman error, but also add in this cross entropy term to be able to predict which behavior a given state came from. Then once your value functions can help you identify behaviors, from that point, at test time, you can, at every time step in real time, pick a behavior to execute by sampling from the softmax distribution, and then sample an action from that behavior, execute that action, and then optionally fine-tune the behavior that you selected on your most recent experience. Cool. And this allows us to actually adapt in real time, both at a high level by selecting different behaviors and at a low level by fine-tuning the parameters of those behaviors. Now, in contrast to prior works, some approaches in hierarchical reinforcement learning will try to learn a high-level controller that predicts the low-level skill to use. And in contrast to those methods, we don't actually need to train any other neural network on top of the policies and value functions. And so this is much more lightweight. It's also agnostic to how the policies and value functions are trained in the first place, whereas like approaches like meta-RL require the policies and value functions to be trained in a very particular way. And lastly, it's a fairly simple mechanism for allowing robots to adapt within a single episode in real time. Cool. So let's look at some simulated experiments before looking at the real robot experiments. We evaluate the number of time steps it takes for the robot to succeed at the task with under different conditions at test time. Specifically, we're going to look at varying joint stiffness, including varying joint stiffness and ground friction. And in both these cases, the stiffness and the ground friction will be out of distribution compared to what was seen during training. We're going to compare to a state-of-the-art fine-tuning approach, a representative meta-RL approach called RMA, and then also a high-level classifier that simply classifies which behavior to use. Now, if you look at the results, both for stiffness and for friction, where lower is better because this is the number of time steps, we first see that for stiffness, the high-level controller is doing best, indicating that it's better to adapt the high-level behavior. And for dynamic friction, we see that RMA is actually doing it's better to adapt at a low level. And so basically in different scenarios, it might be better to adapt at a high level or at a low level. And then if we look at the performance of our method in yellow, we see that first it actually does the best in both scenarios because it's able to adapt both at a high level and a low level. And it's also actually doing better than the next best approach. And this means that actually by adapting at both levels, we're actually able to adapt more effectively as well. And we're able to adapt around 2 times faster than the next best approach. Cool. What about in the real world? So we took a Go1 quadruped robot. We pre-trained it to with different behaviors. One is just to walk, one is to walk with one leg frozen, one is to walk with a different leg frozen, and so on. And then at test time, we gave it a variety of different distribution scenarios. The first scenario we tested was to put 2 roller skates on the front right feet, the front 2 feet of the robot. The robot had never had shoes on before of any kind, and roller skates are even more challenging. And if you just look at the performance of the walking gait, it really struggles with this sort of scenario. It's not able to robustly handle the roller skates. The high-level classifier also struggles to figure out effective behaviors for the task. Whereas our approach, by adaptively selecting these behaviors in real time, is able to figure out how to handle this sort of out of distribution scenario and adapt its behaviors in real time, and ultimately get to the finish line of the task. Cool. We also looked at carrying a heavy payload on the back left leg of the robot, and it's also able to adapt to this. And this is, I think it's a pretty heavy backpack with like a laptop and a water bottle, I think, as well. And then it's also able to handle a dynamic load. And the reason why it's able to handle a dynamic load and actually go faster when it has a lighter load and adapt its behavior with a heavier load is because it's doing all of this. It's really selecting behaviors at every single time step. And so it's not actually going to be limited to the what was just happening in the very recent past. Awesome. And so the takeaways from the second part of the talk is that for pretty challenging out of distribution scenarios, we can allow robots to adapt to them in real time. And we can do so by adapting at both a high level and a low level. And this is important for handling both large shifts and more subtle shifts. Cool. Yeah, that's it. And happy to take some questions.
We have time for a couple of questions.